What's going on, my friends? This is Dustin Stelzer with Electrician U, and today we have a really cool episode. We're going to talk about lamp types, all the different kinds of lamps or bulbs that there are out on the market, and what the differences between them all are. There are so many different kinds of bulbs or lamps out there that sometimes it can be a little confusing as to which one is which, and like what's the difference between the one that has the big tube in the middle and the skinny tube in the middle, and why does a halogen operate different than an incandescent bulb, and like what is up with the CFL bulb, why is there a little plastic stuff? So we're going to dive into all of that. So first off, is it bulbs or is it lamps? Now, a lot of people call these lamps and a lot of people call them bulbs, and neither is wrong. For instance, when you look at some of the boxes that these things come in, this company is called Fusion Lamps. They are a light bulb retailer. So everything they sell is light bulbs, but they call them lamps. So they call on this package, this thing, a lamp. But if you turn it around and look on the back, it says per bulb on the specs for this specific one. Same thing here. This one says, caution, this lamp is pressurized. But then you look on the specs for it and it actually says in lighting facts per bulb. So even the companies making this stuff are printing both on each box. A lamp, it seems, is really intended to mean a luminaire or a thing from within which lets light out. A bulb is more talking about like the shape of the thing or the inherent nature of the thing itself. Really, you can call it either. I know really old school electricians that love to call them lamps, and they hate when you call them a bulb, and they're like, they're not bulbs, they're lamps, look at the package. And it's like, haha, look at the package, dude, it says both of them. So again, really doesn't matter. This episode is brought to you by Rogers. So if any of you out there are looking to become an electrician, or you are currently an electrician and you're looking to make that change over to the commercial service world, go check their website out and see what they're about. They're a nationwide company, so they have offices and techs all over the US. So they probably have a location near you. If you're interested in knowing a little bit more about them, there is a link in the description below. So let's start with the basics. We've got the standard incandescent lamp. And incandescent is a little bit unique nowadays because everything seems to be gas filled in all of these new HID lamps and the compact fluorescent and fluorescent. And so these are the old school lamps that relied on a piece of metal on the inside to glow, and it glows really, really bright yellow. So if you look closely, you can see on this lamp there is a little piece of metal on the inside, and this piece of metal is actually a lot thicker. It's 40 watts, but it's such a small lamp that to get that light output, they didn't have to create a coil of wire. Whereas in one of these, if you look really closely, that filament on the inside is not just a straight piece of wire that goes all the way through it. It's actually a tiny little coil that is wrapped all the way around this thing. And it's a really, really thin metal, whereas this is a lot thicker metal. So for this to be this small, they just increase the diameter of that filament. They don't run it out so long, so they can balance out and get the same amount of resistance over the course of this whole bulb, so it pretty much puts out the same amount of light. But the filaments actually look a lot different when they're burning. So it's really easy to troubleshoot these because, again, you have a solid piece of metal all the way from the end, from the tip of this, all the way through the bulb and back to the screw shell itself. So troubleshooting them, you can always tell if a lamp's good if you set your multimeter to continuity. You put one lead on the screw shell and one lead on the very tip. And you hear that tone. That lets you know that you're sending a signal all the way through and getting that signal back, which means you have a complete loop. This is the only lamp that's like that. All of the other lamps that we're going to talk about, with the exception of halogen, halogen's really still an incandescent. But the way that halogen works is a little bit different, and I will talk about that in a minute. Some of the things that can go wrong with incandescent lamps are obviously that little filament on the inside can break. I mean, if you shake this thing hard enough, drop it on the ground, you can actually break the filament because it's such a tiny little sensitive piece of wire. So you can hear, like, say you don't have a light bulb that's completely clear like this. Say you've got something that's got like a frosted top or something that doesn't allow you to see it. You can actually shake it and you can hear this kind of soft squishiness that's like the element shaking around in the inside of it. If it sounds kind of soft and squishy, like things aren't moving too much, it's just vibrating and moving around a little bit, chances are that the lamp is good. But I would always check it with your multimeter just to make sure. But if you shake it and it sounds really like trashy and scrappy, like there's just shit bouncing around and hitting stuff in there, chances are it's bad, and I would test it. But that's like a quick way to diagnose by listening. But you're always going to want to pull your multimeter out and just double check it. Some of the things that can go wrong with these lamps are this screw shell. If moisture gets inside the fixture, it creates corrosion, oxidization, and the shell will actually kind of weld itself to the socket, and then you'll be trying to twist it out and it won't come out and you'll break it. So if you break the filament, if you break the socket, or if you even break this envelope, the envelope has an argon gas in it. And the reason that argon is in there, almost every one of these that we're going to talk about, by the way, has argon or some sort of like xenon inside of it. And the reason for that is, in the case of the incandescent, is that filament itself is made of tungsten. And that tungsten over time kind of repels the material that it's made out of, so it creates like soot around the outside of a lamp. If you ever look at like an older lamp and you can tell it's been used and it's like really old, it's got black soot all the way around it. So the reason they put argon in there is to help minimize that a little bit. It's kind of like when you weld, some welders know this, but you put a gas shield around your wire so it doesn't allow oxygen to get in and mess up that weld. They call it a gas shield, but it's essentially the same thing. If you let oxygen get to that filament, that tungsten is going to burn out a lot quicker. So they pressurize these lamps with argon, and that just kind of reduces it. It creates like a protective pocket around that tungsten filament so that oxygen can't get in and as quickly and kill that filament. So it just lets the lamp life last longer, essentially. All right, so the next bunch of bulbs that we're going to talk about are the halogen bulbs. So if you look at a halogen bulb, on the inside there is a glass tube essentially, and then you have outer glass as well. Most halogens are all constructed that way. You can't see inside any of these, unfortunately, but there's an outer glass cover and an inner glass cover. So these are still just like an incandescent. They're going to have continuity. If we try to take continuity between one side and the other side, there's a piece of metal in there. So just like incandescents have a tungsten element inside of them, it's just made from tungsten, halogens do as well. But what sets halogens apart is halogens burn at a lot hotter heat, and with incandescent bulbs, when these are starting to burn out, the tungsten gets ejected from the filament, and it starts to kind of form a ring around the inside of the glass. And that's just because it's like burning a fireplace. You know, you're gonna have soot. It's a byproduct of what's burning inside of here. What makes halogen so unique is you're able to achieve a much higher temperature with a much smaller filament. Inside of that inner tube, that tube's actually made of quartz rather than glass, and because the quartz is so much closer to that filament, it can't be made out of glass, or else the glass would just shatter. So they instead of putting like a normal argon gas inside of that tube, they end up putting a halogen. And there's a bunch of different chemicals in the halogen family. There's like bromine and iodine and chlorine, fluorine, things like that. But they put a halogen mixture on the inside of that, and what that does is, as the tungsten kind of flakes off of that element, and normally would just deposit soot on the inside of that quartz tube, the halogen it takes that soot and redeposits it back onto the filament. So it's a way for that filament to stay stronger a lot longer, and you can produce a heck of a lot more heat and a lot more light with a lamp like this, instead of an incandescent where it's primarily space with a little bit of argon gas and a long, thin filament. With halogen bulbs, like the outside of this, it's okay to touch with your fingers, but you'll get a lot of these lamps that are just that inside tube that you can hold in your hands, and you have to make sure that you wear gloves or something and you don't touch the inner glass. It's a lot harder glass because it can handle the temperature and the pressure of the gas that's inside of here. But when you handle it, it changes the crystalline nature of the outside of this bulb. So it actually weakens that glass, and it doesn't break it, but it does allow it to be a little bit more porous, which allows gas to escape, and over time it's going to make that bulb weaken up. So if you're replacing a whole bunch of these, they come with gloves. I know a lot of people are like, screw it, I'm not going to use those stupid gloves. You need to, because you're actually weakening that lamp. It's like you're taking an incandescent lamp and just tapping it and then sticking it up in a fixture. You can't do that. So these will burn at a really high heat as well. So if you ever have a halogen lamp and you put it in a recessed can and you stand under the thing, you notice you can feel that heat baking you. Like, it's really, really hot. Say that was a 60 watt lamp, and then we took a 60 watt incandescent and did the same thing. You would still notice heat on the incandescent because it's literally just burning metal under you and it's putting off a lot of heat, but it's not going to be anywhere near as hot as a halogen will. And the halogen is a lot more hyper focused light, so it just feels hotter looking into it. It's a lot brighter, and a lot of the halogen bulbs come like with a reinforced kind of metal over the top of them, so that you have an outer jacket of metal that's not as hot, that's encasing the inner metal that is quite a bit hotter. Now, due to the nature of the heat that's inside of this and the pressurized glass, I have found that halogen lamps burn out constantly, like far more than incandescent. There's just not as much heat to have to work with. So incandescent lamps, while they'll start to kind of like discolor and the filament inside of it will weaken over time, the heat alone from these things just cause them to burn out constantly. When you look into these big PARs, not as much. It's really more like the smaller lamps where everything is so compact in there. Next up is the fluorescent light. So a fluorescent tube, probably the most common light bulb used in society, used everywhere, office buildings, restaurants, shopping malls, big box stores, everywhere. How a fluorescent bulb works is very efficiently, but they work with a ballast. So there's no piece of metal that goes all the way through here that, you know, like an incandescent bulb would have to heat up and glow. There are filaments in this though. There's a cathode on each side, and each cathode is essentially a piece of metal that is a coil, like a tungsten filament in a regular light bulb, and then it comes back out the other side. So how it operates is these cathodes, when current is sent through them, they heat up, and they're made of a specific type of material that give up electrons. So as it's giving up electrons, the ballast will send a high voltage pulse through this to try to start the lamp, and it'll send an arc. By sending all of those electrons through the tube, it sends an arc through the tube, and that arc might take a couple of times to strike. Sometimes when you turn these things on, you see them blink a little bit because they're cold and they're trying to start. Once that arc starts, then it starts to vaporize the mercury. There's like a tiny little mercury inside of this thing. But as that vaporizes, the mercury goes into the arc stream. And that mercury gets up to a certain temperature, and the mercury also produces a UV light spectrum. So these lamps can't just work off of an arc being produced out of them. They don't put off efficient enough light because of how far the cathodes are away from each other. Whereas like an HID lamp, you know, something like a high pressure sodium lamp, just the arc alone inside of here is at such a high intensity that is all you need, is that arc to produce the light. While inside of here, the arc's not as strong, so you have to help it glow in some way. And how they do that is through a phosphorus coating. So on the inside of this, the reason all of these things are white is because it's coated with a phosphor powder inside of here. And what's cool about phosphor is when you introduce UV light to phosphor, it makes phosphor glow. So really, these lamps are just phosphor glowing, and that's what's so cool about them. The arc that's going through it is basically just getting the same even amount of light all the way through from one side to the other side. Now these can be at a lot different colors too, like you can see pink ones, green ones, blue ones, and all that is different types of phosphor that are on the inside of this. They can blend one type of phosphor that makes blue light with like something that makes yellow light and, you know, achieve like a green light. I mean, they just take different phosphors, mix them up, and that's how you get things, even from like a cool white to a warm white. But that's pretty much it. There, it's again just sending an arc through a tube, and the tube has gases in it, and the gases produce a certain kind of light. Next is the compact fluorescent. We just talked about the standard fluorescent. These work the exact same way. It's just hence the name. They are compact. And they'll fit inside of a standard light socket. But essentially the same functionality. These are self-ballasted, which means that you actually have a ballast on the lamp itself rather than needing a remote ballast. There are some that are not like that. But instead of you needing a remote ballast, the ones that are self-ballasted actually have all the components small and tight and compact inside of the fixture. But again, the ballast is going to ignite a tiny little spark inside of here. It's going to send the electrons hurling towards each other, and it's going to create an arc inside of here. And once the arc inside of that argon gas stabilizes and starts to heat up, it starts vaporizing the mercury inside of here, and it sends a blue UV light all the way through the inside of this thing. But they put a phosphor coating around the inside of it just to try to balance that color out and make it a little bit more white, because again, the UV light interacts with phosphor and makes phosphor glow. So that is how fluorescents work. What I see as problems with these lamps is a lot of techs kind of abuse them. I've noticed that, and you know, I've done it too, but when one of these is in the socket, guys screw it in just like this with the glass, and then they get it all the way tight in there, and then they try unscrewing it, and they're like yanking on this thing, and then boom, they end up breaking these little points right here. Or they just weaken them enough so that they're like really, really loose, and you could grab it and you could feel like, whoa, this thing's wiggling. So that lamp's not going to last very much longer. You broke the seal, so now that argon gas is not going to be in there. The tungsten leads inside of here are going to become oxidized, and they're going to burn out. Plus, you're not maintaining the pressure for that arc to travel all the way through the tube. So a lot of times in that situation, you'll have a lamp that only glows like a little bit here and a little bit here, but it doesn't fully glow because that pocket has been broken. Beyond that, there's not a lot of problems that you have with these. These are extremely efficient. They don't require a lot of current to go through them to produce a lot of light. Once you get that phosphorus glowing, it produces a lot of light, and it doesn't need a lot of resources to do so. Cool thing about these guys is that they come in a lot of different color profiles. So anywhere from 2700 K or Kelvin on the light spectrum all the way up to probably 6500 K. I think I've got, this is a 5000 K. This is 2700 K, this is 3500, and this is 4100. So the differences in color between these, the lower Kelvin that you are on the scale, 2700, it's going to be kind of a like, haven't drank any water in 3 days, piss color yellow, where it, you know, like orangish, whereas a 3500 is going to be a little bit more of a whitish yellow, and 4100K is going to be more of a yellowish white, whereas 5000 and up, 6500, all that's going to be really, really white, almost tending towards blue. So you want to make sure anytime that you're out at a job and you're like ordering materials or replacing stuff, that you pay attention to the color profile of CFL lamps. Even fluorescent lamps are the same way. Make sure that you're getting the same color profile. And then on the sides of these, not only just color, but there's actual wattage. So you want to make sure you match the wattage, and also very important is to match the lumen output, because you could have two 2700K lamps that are like the same size, but one of them's like 1200 lumens, the other one's 600 lumens. The 1200 is going to be twice as bright, even though it's the same color. So there's a few specs to look out for. When I'm doing these, I always usually just pull one out, take my phone out, snap a picture of the writing on here, and then I'll just have the office try to find the exact part number. That way all the numbers match, and you don't go out and start putting orange lamps in a whole parking lot that needs white lamps, and then you look really unprofessional. All right, so now let's talk a little bit about LED lamps. So you'll notice that LEDs, kind of similarly to a CFL, have a little plastic portion around them on the bases. This one is inside of here, so the diode is really only up front that's emitting light. So an LED is also a self-ballasted lamp. Some of them are not. Some of them have to have a remote ballast to them. A lot of like under cabinet tape lighting and things like that, you have to have a separate ballast because all there are diodes. The ballast has to exist somewhere, even in those CFLs. But with an LED, the way that an LED produces light is different than anything else. So there's two semiconductors inside of an LED bulb. And one of those semiconductors is positively charged and one of them is negatively charged, and they put them together to create a diode. And that's what you would see. Each one of these little 4 yellow things inside of there is a diode. So it's got 2 different semiconductors mixed together. So when current travels through this lamp, what's happening is the negative charges and the positive charges move in opposite directions. So they're actually moving towards each other on these 2 different plates, essentially. And when they combine, they emit a light. There's a loss of energy that happens. So they have to, the energy has to go somewhere, and when it does, it comes out as visible light. LEDs can actually produce different colors, similar to how a fluorescent fixture would do that. There's still phosphides inside of them. So there's an indium gallium nitride and an indium gallium phosphide. And between those 2, they're able to achieve different colors just by mixing those chemicals in. And then there's even some things that there's a controller, and you can control like the entire light spectrum. And usually what they're doing in a light like that is they're putting multiple different diodes together that are each tuned to specific color frequencies, and then they have control. After they have those different colors in there, they have the control of mixing them together to produce pretty much any color that they want to. So a lot of hodgepodge science, I guess, but it's basically just finding another way for light to be repelled or light to be expelled out of something. And that's how all of these work. It's either an arc going through a gas, it's running current through a piece of metal and letting it glow red hot, or it's putting 2 semiconductors together and having an interaction between positive and negative particles that produces light when that happens. So you'll notice too, not so much on this one, this is a really low wattage lamp, this is 7 watts, but you'll notice on something like this where it is 12 watts, and it's not even so much the wattage, it's the size of the diode, the amount of heat that it produces. But a lot of LEDs have these heat sinks around them. So it's just metal, extra metal with holes in it all the way around so that heat can escape. But the process that that semiconductor is going through is a really, really hot process. And LEDs, funny enough, are actually some of the hottest types of bulbs out there, but because they have these heat sinks on them, it dissipates that heat really efficiently. So they're actually cool to the touch, and you could have a light bulb on above your head and touch the thing and it's not going to burn you. Whereas like a halogen or an incandescent or a metal halide or high pressure sodium, like they can get up to 700-800 degrees and burn the shit out of you. So that's pretty much how LEDs work. They're super efficient. They're always low wattage. A lot of the packaging comes in like replacement sizes, so you can have a LED that is, I don't know, 7 watts. What would a 7 watt be equivalent to? I don't have the package, I don't know. But essentially 7 watts would be like the equivalent to like a 60 watt lamp, somewhere in that range, plus or minus a little bit. But look at your equivalency too. So if you know that a customer of yours has 60 watt lamps and everything, or 75 watt lamps and everything, when you go to buy LEDs and do retrofits, make sure that you're getting the same relative wattage, the same relative amount of light in both lumens, color, and wattage that they had before. And that may take a little bit of looking up on Google. Google's your friend when you're out in the field if you didn't know that by now. But that's everything about LEDs. All right, so the next type of lamp that we're going to talk about is the metal halide lamp. So metal halide is from the HID family. HID lighting means high intensity discharge. Essentially, these work very similarly to a fluorescent lamp. You're sending an arc through a tube. That tube has a certain gas in it that's able to produce a really high intensity arc. And through controlling the substances that are inside of that tube, you can control the color and the temperature of that tube. So essentially how an HID probe start bulb works is you've got electrodes, one on each side. Those electrodes are essentially just filaments. And then you have a starting probe as well. And that starting probe has a starting resistor. But when current starts to go through this lamp, basically inside of the bottom of it, you have this little arc that happens. And that arc will ignite the argon gas that's on the inside of this. And it starts to heat up to a point where there's a small trace amount of mercury inside of here, just like a fluorescent bulb would have. But that mercury starts to vaporize and create an arc all the way across this tube from one electrode to the other electrode. And it's a really low blue color, so you'll notice when these first start to turn on that it's just this low, barely an arc at all. It just looks like a stream of low blue light, and that's the mercury. That's the color that mercury burns. Now in the inside of this tube, you have this cloudy kind of film all the way around that inner quartz tube. What that is halide salts. These are called metal halide lamps. So halide salts are certain chemicals that when vaporized, they will start to kind of change color. So instead of like a fluorescent lamp relying on phosphorus to get its luminescence from, the arc alone inside of here is bright enough to strike a light, but they want to kind of control the color output so that it produces a certain amount of light and a certain spectrum of light, really. So these burn at about 4000 K, which is a pretty white color. But those halide salts that are on the inside of this each have kind of their own color profile. So once each one of those halide salts vaporizes and gets entered into that same arc stream that's inside of here, it changes the color of that arc. And it goes from that low blue to kind of like a pinkish and then a purplish, and then it all of a sudden dissolves into white, like really brilliant white light. And that's when all of the halide salts are evenly burning. So another note on that, if you notice, most metal halide lamps have this white paint at the top and the bottom of each one of these quartz tubes. Reason for that is that white reflects light. So that's like when you're in the summer, if you're wearing black, you're going to be really hot, but if you're wearing light, a lot of that gets reflected off of you. So the reason that needs to happen is that some of those halide salts inside of here have to maintain a certain temperature. And if they get down below a certain temperature, you'll see the color start to shift inside of the lamp, and it becomes really unstable, and it just color shifts a lot. So for the color to stay a stable white, you need to maintain a certain temperature inside of there. So what it does is all of the heat that comes off of this lamp, about 25% of it will go back into the lamp to maintain the temperature of the arc. 75% of it is wasted as heat, but another 25%, when you paint the white, it reflects it back into the tube so that that amount of heat is able to stay in the tube and stabilize the color of that arc without it shifting on you. Every one of these bulbs is going to have a mounting position in them. So like this one says U, it says 1000 watts / U. So U means universal. It means you can mount it upside down, you can mount it sideways, upward, doesn't matter. The arc is going to act the same way in that tube regardless of how the thing is mounted. There are some things that are meant for mounting upside down or base up. And the reason to that is if you strike an arc in there and you were to turn the lamp sideways, the arc would dip because of gravity. It's going to dip in the middle, and it's going to be arcing against the side of that inner quartz tube, and it's going to heat that quartz tube up to a point where it's going to weaken it, and eventually it's going to burn out or have like an explosive death. A lot of these tubes get so hot that they will blow up. And so you got to make sure the mounting position on all the lamps that you're getting is specific to its purpose, or that it's universal, meaning that the lamp's designed to be used in any way because of the characteristics of how they designed it. It can handle that. Next up on our list is the high pressure sodium lamp. So high pressure sodium is another type of high intensity discharge, much like the metal halide, but you can tell that the arc tubes are completely different. So a high pressure sodium has a lot skinnier type of tube, and you can tell that tube is not clear. It's not actually made out of glass or quartz. And the reason being is with sodium and mercury on the inside of this thing, you have to have such a high amount of heat that glass or quartz would just break. So what they did is they came up with this specific type of ceramic. It's like alumina oxide ceramic, and that is what that whole tube is made out of. Now the base gas, rather than it being argon in this tube, the base gas that arc has to go through is actually xenon gas. And so it operates very similarly to any of the other HIDs, but what makes it different is you have to send a high voltage pulse through this to be able to ignite an arc to get through this material. The inner tube is filled with xenon instead of argon, like a lot of incandescent and fluorescent lights, but that xenon is what the initial arc is stabilized through. And then there's mercury inside, just like almost all these other gas type fixtures. But there's also sodium. So sodium burns at like a really yellow color, especially like the low pressure sodiums before these high pressure sodiums came out. And the mercury also has like a bluish color to it. So when you mix the two of those together, you actually get this kind of like golden orangish white color. And the advantage of that is a low pressure sodium lamp or any other just regular type of sodium lamp puts off a really yellow light, and it makes everything around look extremely yellow. But mixing mercury with that blue spectrum and the sodium with that yellow spectrum, when you mix them together, you get kind of a whiting effect that allows for yellow light to be around, but you can still tell the color of the things that you're looking at. Not everything just looks yellow. It's yellow light, but you can still tell the color of everything around you. So that's the purpose of this lamp. So the process for how this works is the ballast outside of here actually has an igniter. A normal metal halide fixture is not going to have an igniter to it. That's how you can tell the difference between the two ballasts when you're looking at them. That igniter, once current is run through it, sends a high voltage pulse of current through the lamp to strike an arc. So that tube inside of here, the base gas that's inside of the tube is xenon. And then there's two other types of gases that are created once the heat inside of that the tube rises. The first one is mercury, just like all these other types of lamps. That mercury gets to a certain temperature and it starts to vaporize into that arc stream, and the sodium does the same thing, but the mercury is a little bit lower temperature when it burns, so it burns first. And then once it gets up to a certain heat level, then the sodium starts to burn. So you'll start to see when this thing ignites that you've got this like baby blue color once that mercury starts to ignite. And then once the sodium starts to ignite, you'll start to see it's shifting colors to much more of a yellow color. These bulbs get very hot to the touch. So I mean, like, you could melt your skin because it's like, depending on the wattage of the lamp, the size of the envelope, everything, and whether or not it's mercury vapor, metal halide, or high pressure sodium, they can get anywhere from like 400 degrees Fahrenheit to 800 degrees Fahrenheit to the touch. So just be really careful working on these. High pressure sodium, you can tell when the lamps are starting to fail because they cycle on and off. So you'll see if you stand in a parking lot for 30 minutes and just sit and watch one of these lamps, it'll shut off and it'll be off for like, I don't know, 10, 15 minutes, and then it'll start to ignite again, and it'll get up to pretty close to full bright, and it might even stay there for a minute or two, and then it shuts off again. And it just keeps doing that over and over and over, where a metal halide's not going to do that. So that's how you can diagnose whether or not a high pressure sodium lamp is your problem. So the next type of lamp I'm going to talk about is another bulb that's in the HID family. So this is the Mercury Vapor lamp. So all three of metal halide, high pressure sodium, and mercury vapor all utilize mercury inside of them. That's really the only thing that they have in common, except for the fact that they're igniting an arc through a gas. What's unique about the mercury vapor, though, is it only needs that mercury in the tube to produce light. The other ones, high pressure sodium, it's utilizing mercury and sodium, and the gas that's inside of it is xenon rather than argon. This just has a little bit of argon in the central tube, and then it has a little bit of mercury in it. So you still send this with a pulse, and you ignite an arc from the bottom electrode to the top electrode. And once that argon gas and that arc get hot enough, it starts to vaporize the mercury inside of it, which lets off a blue light. But everything stops there. It's just a blue light. It's just mercury, that arc, and that's it. So you'll see a lot of the clear mercury vapor, not the ones that have a phosphor coating like this, but a lot of the clear ones will burn like a hyper blue light, and they're like 6500 K on the spectrum, so really, really blue. What they've done with a lot of these other ones is to still kind of get a white light out of it, something that's back more in the like 4000 K color, is they put phosphor around the inside of this just like they would on a fluorescent lamp. And what that does is it mixes that blue light with a little bit of white. Again, the mercury on the inside of that tube is producing UV light, and when you shine UV light on phosphor, it makes the phosphor glow, so it gives it almost a fluorescent kind of feel, but it's a different spectrum of light. So you can't see this here, and unfortunately I don't have a clear mercury vapor lamp, but if I did, what you would see is essentially this exact same thing. It's going to look like a high pressure or a metal halide lamp, but you're not going to have the white coating that's painted on the tops of that quartz tube because it's not necessary. Remember, the only reason that that white coating is there is because some of the halide salts for the metal halide light specifically have to have that coating so that it maintains the arc and those colors don't start fluctuating, because those specific halide salts have to have that white coating. So on a mercury vapor that's clear, it's just going to be a clear tube, and that's it. There's no need to have anything else. It's just mercury burning through it, and you want that blue light. So that's pretty much it. There's a lot more bulbs and lamps that I could have talked about. There's like hundreds of more. But really what I wanted to do is at least just do kind of a basic outline of all of the different families of lighting. So obviously we have the incandescent family and the halogen family and the LED family, the fluorescent family, and the HID family. Most of what you're going to come across out in the field, with the exception of neon lighting, which is still just very similar to how fluorescents work, but most of everything you're going to come across out in the field as a service tech is going to be within these families. There's tons of different shapes of lamps that are, smaller and bigger, and they have different pins in them. Some of them have like a socket that looks like this, and some have a socket that looks like this, but within all of that, you're still in these same families. So thank you guys so much for watching. If you have any comments at all, any questions, anything you think I missed, or anything you'd like to know more about, please leave some comments below. I love you crazy people, and I will see you in the next episode.